Okay, so today we're going to graph and analyze rational functions, and they are going to have vertical, horizontal, and or oblique asymptotes. So there's going to be a combination of them. We just get the door for me, Jonathan, or Nolan. Thanks. Okay, so in the last section, we graphed the reciprocal functions. Those are a simple form of rational functions. And then today we're going to find functions that have this form of f of x equals a of x over b of x is what they call it. So a of x and b of x are both polynomial functions. Last time we did this, we only had a polynomial function on the bottom, and then we had a number on top. Now we're going to have an expression on top. Okay, so just like before, whenever you have a fraction, the denominator can't be 0. Okay, so you're going to be asked to find zeros and asymptotes. This is going to be your form, and if you are finding a 0, then you set the numerator equal to 0. So they call the numerator a of x. So you're going to set that equal to 0 and solve for x. Okay, these are also called just zeros of the numerator. And remember, zeros are the same thing as x-intercepts. Okay, we are familiar with finding vertical asymptotes. That is when you set the denominator equal to 0. So you would set b of x equal to 0 and solve for x. Okay, and so these are called zeros of the denominator. Okay, that's also going to be where your function is undefined for those values. All right, now that we're in a different form, there is going to be a new way to find horizontal asymptotes. Before it was always added on the outside. That is not going to be the case anymore for this form. Okay? So notice that in all of these, it says if the degree of A, if the degree of A, if the degree of, and this should be A. So the last book called it P of X over Q of X. This book calls it A of X over B of X. Okay, so it's all about the degrees, and you're comparing the degrees of the numerator and the denominator. Okay, so if the degree is greater than, the degree of A is greater than the degree of B, that's our first situation. Our second situation is if the degree is less than, and the third is when they are equal to. Okay, so these are the three different cases. It can either be the numerator is greater than the degree of the denominator, and if that happens, the horizontal asymptote is none. There would be no horizontal asymptote if the degree of the numerator is greater than the denominator. Okay, if the degree of the numerator is less than, then we say y is equal to 0. That is your horizontal asymptote. And then the last one is going to be special. So if they are equal, you form this by creating a fraction where the numerator is the leading coefficient, so I'm going to call it the LCO of the numerator over the leading coefficient of the denominator. So if the degrees are equal, you take the leading coefficient of the numerator and you put it over the leading coefficient of the denominator. So we're going to do an example of that one. There's so many different types of graphs for this that we would be taking notes all week if I showed you all the different types. So we're going to do a quick example so you can see what happens here. Okay, so an example would be you have f of x equals 2x plus 1 over x plus 1. Okay, if you are going to find the horizontal asymptote, the first thing you would do is say, okay, what's the degree of the numerator, what's the degree of the denominator? These are both linear. What's the degree of a linear function? Yeah, what is it? 1, right? So if they're the same, when you're setting this up, you just have to take the leading coefficient. Do we remember what that is?
Of x.
Yeah, in this case it's 2. In the numerator, what's the leading coefficient? Nope. Or sorry, denominator. 1, yes. Okay, so the leading coefficient here is 2, the leading coefficient here is 1. What's 2 divided by 1?
2.
Yep, so then this would be your horizontal asymptote, which I call ha. Okay, so if they're equal, you always just take those and make the fraction out of them, okay? Alright, so for example 1, it says find the zeros and the asymptotes of each function, then you are going to graph it. So when you're doing this, the first thing we like to do is find the zeros. Okay, for the zeros, you always take the numerator and set it equal to 0. Okay, which means you get x is 2. Now a 0 is a y-intercept. It's a point. So your point is 2, 0. Okay, so your 0 is your x-intercept. Okay, and then the vertical are what we're used to seeing. Okay, so for the vertical, you're going to take the denominator and set them equal to 0. When that happens, you really should factor this. X squared minus 1 factors into what? X plus 1, x minus 1. It's the difference of 2 squares, right? So for this graph, you haven't seen one like this yet. When you solve this, you are going to end up with 2 vertical asymptotes. So this one, if you set that equal to 0, you would get x equals negative 1. And for this one, you would get x equals 1 when you solve. Yeah, but these are going to stem from the 2 different things. Okay, and then for the vertical asymptotes, the graph never crosses those. So that's the same as what we did for the reciprocal function. Okay, so the graph never crosses vertical asymptotes. Okay, now for horizontal, remember, you are comparing the degrees. So if you look at the numerator, what is the degree? 1. It's linear, the degree is 1. Remember, the degree is just the what? Highest exponent. So in the denominator, what's the degree? 2. Okay, so in that case, the degree of the numerator is less than the degree of the denominator. I just abbreviate. Degree of the numerator is less than the degree of the denominator. Okay, so let's look back up and see what happens. If the numerator is less than, then the horizontal asymptote is
0.
Y equals 0. Okay, so we are going to put that on our graph as well. Now, this is something different. So before, when we were graphing these, with the reciprocal functions, it would not cross the horizontal asymptote, but what's special about these graphs is the graph can cross this. So the graph could cross a horizontal asymptote. Now it's not always going to happen, but in this case it does, and in other cases it does. Okay, so when you're getting ready to make your graph, you are going to need to examine your table and be able to come up with some good points on there. So this table is going to be massive. But we're going to talk about what values are useful and how to navigate that. So I always like to put on mine where the vertical asymptote is, okay? When you're looking at those on your chart, that's where an error occurs. Okay, give yourself some room in between those. So because you have two of them, this divides your chart into how many different parts? 3. So you want to see what's happening to the left, in between, and to the right of your asymptotes. Okay? Jackson, why don't you turn it down? Okay, so once you have this, now you can put in your values. So we are going to use our graphing calculator. If you don't have yours today, then I'm going to have you get a Chromebook and get on Desmos, or else you're just going to be sitting and watching and not be able to pick out the points. Okay, and then when you are putting this in your calculator, make sure that you have your parentheses in the correct spaces. Okay, so you have to do parentheses for the numerator and for the denominator. And then when you're plugging in the denominator, I would plug in just the binomial here. If you plug it in factor, that's fine, but you have to do the double parentheses in that case. Okay, and then go ahead and go to your chart. Okay, so go to your table. And I'm going to have you look at the graph first because you haven't seen this yet. Okay, so go ahead and press your graph. Okay, so you can see that this is a different type of hyperbola. Okay, so before with the reciprocal functions we had the 2 branches. This one's going to have 3 branches. Okay, all of your graphs will have at least 2 different branches. Okay, so we're in our standard window. That's going to work, so we can leave our scale the same. And then let's go ahead and see what's happening in our table. So between these two, obviously we know 0 is in between them. So 0, 2 is going to be helpful. But remember, when we get close to your values, the other values that we found helpful is seeing what happens at a half, at -1/2. Those are going to help us. Okay, so 1.5 would be useful. Okay, at 2 we're at 0. We already know that because that is our x-intercept. Okay, at 3 we're at 0.125. Do you guys know what 0.125 is as a fraction? Yeah, good. Okay, and then on the other side, again, we like to see what's happening at that halfway point. When you see that at -2, you have negative 1.33. And then all of these are really close together, so I might just do the negative 4. You wouldn't have to do that. I just think the negative 0.4 is going to be a little bit easier to graph. Okay, and then let's go to our table set. So if I want to see what happens at negative 1.5, I can just put that in. At negative 0.5, I'm at 3.33. Here I'm at 2. Okay, and then when you are graphing, let's start by putting in our vertical and horizontal asymptotes. So I'm at negative 1. All of these numbers that I have are less than 5, so I'm going to keep this scale. As we progress further, we are going to talk about scales and what you can use, because there are lots of different options. And then we also have the y equals 0 here. Okay, and then we're going to go ahead and we're going to plot our points on there. So the first one I actually plotted was the 2, 0. 1, 2. So remember to count from here, because sometimes it can be easy to center yourself there. At 1.5, I'm at negative 0.4. 2, I'm at 0. 3, I'm at 1/8. And so this here is creating your first branch. It's going to follow that straight across. Okay, and then you can, so we're going to talk about some of our other points here. So at half, I'm at 2. At 0, I'm at 2. At negative half, I'm at 3.33. Now, this is not going to be a straight across line. We know that we didn't see that on the graph, right? There's nothing that goes straight across. So when you want to see like what's happening in between 2 points, this is 0.5. What would be a halfway point? What's half of a half? A fourth, right? So yeah, 0.25. So if you want to see what's happening there, you could also check that out, which is at negative 1.9. So it is really close there. Okay, but if you just wanted to put that 2 on your graph to say, hey, I graphed this, now you have this curve that you can graph. Now this isn't a perfect parabola, that's fine. It doesn't look like one on our chart either. Okay, it is a U shape. And then we're going to use the rest of our points to create the last branch. So at negative 1.5, I'm at negative 2.8. And then you're at negative 1 1/3. And then you have your last branch here. All right, and then you have your graph. How does yours look? So see, like here, it is, we know that it's going above this because it has the 0 there. This would also be a situation where you could trace it and see that it is going above your line, above your y equals 0. Okay, so it's above that. All right, so for part B, I'm going to have you do the zeros, vertical, horizontal, so you can go ahead and write those down. Okay, So whenever you're finding the zeros, it's always the numerator equals 0. So how would you solve that for x? What would you do to both sides? Yeah, take the third root, the cube root, and the cube root of 0 is 0. Okay, so that means 0, 0, that is your x-intercept. Okay? Okay, and then for the vertical, you always set the denominator equal to 0 and solve, so go ahead and solve that. And then you can determine the horizontal. All right, so there's two ways that you could find the vertical. Did you guys just subtract 2 and then divide by 2? Okay. Did any of you do anything else? I wasn't sure if you guys were in factor mode where you can take out the 2, right? And then just divide by 2. X plus 1 equals 0, so x equals -1. Either one is fine. Okay, so x equals -1, we know we're going to put that in the center. Okay, so for the horizontal, you compare the degrees. So the degree of the numerator is what? 3. What's the degree of the denominator? 1. So you just have to compare them. Numerator degree, denominator. Which one is bigger? Numerator. So if the degree of the numerator is greater than the degree of the denominator, what is the situation? What does it say? Then there's none. So if the degree of the numerator, that's your A, okay, is greater than the degree of the denominator, then there is no horizontal asymptote there. So we only have that vertical asymptote. Okay? I saw some of you guys starting your chart, and that looked good. You guys put the x equals -1 on there. Okay, we know that's where the error occurs because it's undefined for x equals -1. So when we want to see what happens next to it, right, if it's -1, remember we do the -0.5 and the -1.5. Then we can go up to the whole numbers. We know at 0 that the y is 0 without even graphing. We already found that, right? Okay, so let's look at our table. So when you plug this in, because it is only one term on the top, you don't need parentheses there, but you do need them for the denominator. Okay, and then my table set, I'm going to start it, back at 0, and then go by ones. Okay, so it looks like these are all going up, right? So it's 1, 3, 6, 10, 15, 21, 28, 36, 45. So if I wanted, I could make it go up by a lot, or I have enough here. Let's see what it looks like. What did you guys think when you saw it? That you did something wrong? So there are 2 branches, right? Okay, so you can see the 2 branches. So if you see the 2 branches here, then that's fine. You know that we can use this as our window. And so when we're setting up our table, right, at 1, we're at 0.25. At 2, we're at 1 1/3. Maybe I skip the 3 and just go to the 4, the 6.4. And then let's see what's happening on the other side. So at -2, I'm at 4. At -3, I'm at 6.75. All right, and then, so all of these values are positive so far. Okay, we can see in our graph it is dipping into the negative, so let's get some of those values on there. So we have the negative 0.5, I'm going to go back. So there's that negative 1/8 again. Okay, so all I have to go to is I have to make sure it's at negative 1/8. So when I'm creating my grid, I'll just keep that in mind. Okay, and then we always want to start with putting our asymptotes on there. So it was at negative 1, so we just have one vertical at x equals negative 1. And now I'm going to graph my point. So I usually start with the intercept, the 0, 0. At negative 0.5, I'm at negative 1/8, so that's small. And then again, if you want to see what's happening here, you could always do like negative 3/4, right? 0.75. That's still not, it's still not even to negative 1. Okay, but you can see from your chart that this is going straight down from your graph. Okay, and then at 1, I'm at 1/4. At 2, I'm at 1.33. At 4, I'm at 6.4. Okay, so this is creating this branch of my graph. Okay, and then at negative 1.5, I'm at 3.3. Okay, so then I have these points here. Again, it's going to be helpful for me to see like where I'm curving this up, because I can see on my graph it's a curve. So a good thing to check would be like negative 1.25. Oh, maybe it's on there. Maybe it's not. So I can always just type in where I want to start. So that's really close to 4, right? Right here. And the reason why I'm adding those points in is just so I can see, okay, this is where it's going to make that U shape, what's really kind of like a V shape, which we're going to see more of in the next graph. Okay, so that just helps me create that curve.
So the top one go over that.
Nope, so it will never cross a vertical, it can only cross a horizontal. Yep, so it'll never cross a vertical, but it can cross one that's horizontal. Okay, good. Other questions for me on that? All right, and then we're going to learn about a new type of asymptote today. It's called oblique asymptotes, or a slant asymptote. It is not vertical, it is not horizontal. Okay, they are formed under these conditions. We're going to talk more specifically about what it is. Okay, it really is a slanted line, which is, a slanted line is what type of function? Linear. So we're going to talk about why that happens. So you can only have an oblique asymptote if you have the following conditions. The degree of the numerator is 1 more than the degree of the denominator. Okay, and the numerator and the denominator will have no common factors other than 1. That means there'll be no like multiples, GCFs that you could take out. One would not go into the other one evenly. And when that happens, we can find an oblique asymptote using something that we did in the first semester. Who remembers long division? Everyone, great. Okay, so long division with polynomials is what we're going to do to find these asymptotes, and it's only equal to the quotient, so with no remainder. Okay, so you don't include the remainder in your asymptote there. And since the difference of the numerator and denominator is 1 degree, what type of function has a degree of 1? Linear. So whenever you write out an oblique asymptote, you're going to write it in the form y equals mx plus b. Okay, first it's always going to be in that form. You're just going to put the y equals on. But then this is a really easy form to graph in, because when you're graphing, where do you start? B. So you always start your graph at the y-intercept. And then you're going to use your slope to find the other points. Okay? We even did that at the beginning of this year, but that was big in Algebra 1. So the next question says, what can we say will always be true of a graph with an oblique asymptote as a result of the numerator being 1 degree greater than the denominator? So let's think about this. We talked today about if the numerator is greater than the denominator, what happens? Right, there's no horizontal asymptote. So since the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote with an oblique asymptote. I'm just going to abbreviate. So if there is an oblique asymptote, there is no horizontal. There can be a vertical, okay, but you most definitely will not have a horizontal with an oblique. Okay? So we're going to graph the oblique one. It says find the zeros and asymptotes of each function, then graph. Okay, so when you're finding the zeros, we always take what and set it equal to 0? Always take the, which part? Numerator. Okay, and then how am I going to solve this for x? Yep, take the square root. And the square root of 0 is just 0. You don't have to worry about the plus or minus. And then when you add 4 to both sides. So remember, this is our 0. This is our x-intercept. Okay, and then for the vertical, we always take the denominator, set it equal to 0, so we know that x is -2. Okay, so for this one, we always want to compare the degrees of the numerator and of the denominator. Now, we can see the bottom is linear, so we know the degree is going to be 1. But when we have this numerator here, we are going to want to multiply it out for several reasons. Okay, because a lot of you already know what's the degree going to be of the numerator. 2. Okay, but we are going to need to expand the numerator. So x minus 4 times x minus 4. Will you guys FOIL that? Write it above. So don't wait for me to do it, you do it. Okay, so x times x was x squared. Add the like terms. What's your middle number? Negative 8x, and negative 4 times negative 4, 16. So you can obviously see your degree is 2, which means the numerator is greater than the denominator. In that case, there is no horizontal asymptote. Okay? Now, when you have this, you can ask yourself, is there an oblique asymptote? And yes, only if there's a difference of 1 degree and the numerator is bigger. Okay, so the numerator degree is 1 more than the denominator. That's the condition. The numerator degree is 1 more than your denominator. Okay, so when that happens, we get to do long division. So when you're doing long division, you want to put this polynomial underneath, okay, which is why you want to FOIL it out. And do we remember how to start long division? What we ask ourselves? So what do you mean by match? Yeah, what times x will be x squared, so x times x. You can also do x squared divided by x, and then we have to do what? Distribute, multiply. X times x is x squared, x times 2x. Okay, now when you do long division, you always subtract, so you distribute the negative. Negative 8 minus 2 is negative 10. And then you start your whole process over again. So what would you multiply by x to get to negative 10x? Negative 10. Negative 10 times x, negative 10x. Negative 10 times 2 is negative 20. And then when you distribute a negative to something that's already negative, it becomes positive. Okay, so we can't go any further, which means this is the remainder. Remember, the quotient does not include the remainder. So your oblique asymptote is just your quotient with y equals. So it's y equals x minus 10. Okay, that's your oblique asymptote there. Okay? Alright, so we are going to graph this. Okay, and just like before where you have like that negative 2 in the middle, where you have your error, same thing. Okay, so we're going to look at the chart before we make our scale. Something different is going to happen with this one. Again, you can either put it in like this with 1 parenthesis, or with this you have to do double. So you can choose which one you want to do. Okay, and once you got it in there, go ahead and hit graph. Okay, now every hyperbola has at least 2 branches. Can you see 2 of them when you hit your graph button? So you can see part of 1, right? Okay, so what we want to do is you can either adjust the window yourself or we can go to zoom out. So if you hit zoom and 3, it'll zoom that graph out for you. Okay, and then we can go to our window and make adjustments from there. Okay, so again, I just pressed zoom. I went to zoom 3. If I hit it again, it's going to zoom it out even more. Okay, so you can see what that looks like there. Okay, so I'm going to go to my window. Okay, I don't need to make it that big. Maybe I would do like negative 100 to 100. But instead of going by 1s, let's go by 10s. I can do negative 100 to 100 here. Go by 10s. Okay, so this is the shape that you should get for the oblique graphs. Okay, so this is the shape that you should get. So see how it looks like a V here and a V here? And there's a space in between them? That's exactly what will happen. So remember, I made my window by 10, so when I do my table, I'm going to go by 10. So I have 0. I'll probably actually go by 1s at first, and then I'll show you how we can do that. Okay, so let's look at, instead of doing the halves, because I'm going to go by 10s here. You have negative 1, 0, 10 is what I'll do. I'll come back and do these. So if you go by 10s and you start at 0, you're at 8, 0, 8. At 10, you're at 3. And then see how these are escalating quickly here? So maybe you could do 40. You're at 30.9 there. And I can come back and add more. So again here, like I would probably do negative 3 to see what's happening right next to it. But then at negative 10, I'm at negative 24.5. So instead of doing the halves like I did before, because I'm going by 10s, I'm looking at the numbers right after them. So negative 20 is negative 32. Negative 30 is negative 41. Okay, and then just like I went by 10s on my scale here, I am going to go by 10s on this scale here. So let's get these few more. So at 1, negative 1, I'm at 25. Negative 3, I'm at negative 49. Okay, so if I'm going to make it up to those taller values, the larger values, I'm going to make a larger graph. Okay? Alright, so from there, I'm going to go 10, 20, 30, 40, 50. This is going to be at 60. My Y. 10, 20, 30, 40, 50, 60. Okay, so when I put in my asymptote, the negative 2, this is 10. So negative 2 is going to be really, really close to my line, Y equals 0. Okay, and that's x equals negative 2. And then when I'm graphing for the oblique, I'm going to start at negative 10. So this would be negative 10 if I'm going by 10s. Now, what's your slope here? What's your slope? 1. So when you do the rise over the run, you do 1 over what? 1 over 1. If I did 1 over 1 and this was by tens, I would have a bunch of tiny, tiny little dots, right? Okay, so instead of going up 1 over 1, can't we just do something equivalent? Like, can't we do 10 over 10? Because 10 divided by 10 is 1, right? Okay, so if I start at negative 10, I'm going to go up 10 over 10. Up 10 over 10. And then again, this is a dashed line because it's an asymptote. And now when you start to plot your points, you're going to see how nicely these fit. Okay, so at negative 1, I'm at 25, which is about right there. At 0, I'm at 8. At 10, I'm at 3. And at 40, 10, 20, 30, 40, I'm at 30.9. Now, can you guys see on your graphs how that follows your asymptotes here? And you're connecting it with a curve in between. So it should be following that V shape. Is that what your guys did? Did you finish graphing yours? Okay, and then let's do the other branch. So at negative 3, I'm at negative 49, which is almost 50, right? So like right there, do you see how it's right inside that vertical asymptote there? That's good. At negative 10, I'm at negative 24.5. So it's almost 25, which would be about right there. At negative 20, I'm at negative 32. And at negative 30, I'm at the 41. Okay, and then again, if you wanted to see what's happening between any of those, you can, but this is going to follow those two curves. Okay? And then, so I labeled this. I'm also just going to label my other asymptote, the x minus 10. Okay, and then of course when you're doing your practice, you are going to be doing this on graph paper.